Okay, I have one more canonical problem I'd like to talk to you about, and this is called the knapsack problem. Technically, this is the 0-1 variant of the knapsack problem. Knapsack problem. 0-1. So 0-1 version of the knapsack problem. So here's the basic story that goes along with the knapsack problem. I'm a thief. I break into a house and I have a bag with me, right? I've got a knapsack that is slung over my back, and I have to choose what to take. So I have limited time, and I need to pick the things that A, fit in the bag, and B, have the largest value, right? So I have an objective, which is to take the most valuable stuff, but I also have a constraint that says, maybe I can't fit the huge television into my back, and instead I should prioritize other stuff. Okay, so mathematically, this is how this goes. I have a collection of n items. For each item, I have a value, right? So n items, I'm gonna call these 1, 2, ... all the way up to n, and I'll call that set capital N. For each item in the set, I have a value, right? So n values, or I should say for all I in my set n, I have a value vi greater than or equal to 0. So this is, I have v1, v2, ... vn values, right? And so this is how much the thing is worth when I'm the thief trying to steal it. Also for each I in n, I have a weight. So weight 1, weight 2, ... weight n. So these are all called the weights. Okay. And I have a capacity of my knapsack, right? And so I have W greater than 0, capacity. So the question is, which of these n things should I take, given that I can only take a total weight of capital W, and that I want to maximize the total value, right? So mathematically, what I would say is I want to maximize over all subsets of n. So maximize where k is a subset of n, the sum of the values of items in k, right? So I in k, vi, right? So all this is saying is that I want to pick a subset of the items such that this thing is maximized. The sum of everything that I've taken, of the value of everything I've taken, is maximized. And then, in optimization notation, I write subject to, right? So this is subject to, is what ST stands for. Subject to the constraint that the sum of the weights of everything I take cannot exceed the capacity of my knapsack. So subject to the sum of everything that I take, sum of I in k, wi, has to be less than or equal to my capacity, my overall capacity, right? So this is, take as much value as you can. As possible. And this is don't overflow the knapsack. Okay, so this ends up being another problem that has algorithmic challenges, but it has them in a different way for slightly different reasons than the traveling salesperson problem. And we can actually get closer to optimal solutions with this one than we can with TSP. And we'll postpone most of that discussion until the end of the course. But this is one where we actually have reasonably fast algorithms that get reasonably close, right? We don't have perfect algorithms, they get perfectly close, but we can do better at least than we can with TSP for some fundamental, as far as we know, some fundamental reasons. So let me present a quick example problem here, just so that we have something in mind, and we'll revisit this example a number of times. Right? So here's my example knapsack problem. All right, so suppose our capacity is 10, all right? So capital W is 10, so let's visualize the knapsack. Knapsack. And so this is, W equals 10. And you can think of the height here as being 10. Okay. And so we're going to be kind of abstract about this, but let's go forward. So the first item that we have has a pretty large weight, so it has a weight of 7. So this is weight 1 is 7. Actually, let me make this just slightly larger so that I can write these things more clearly. So weight 1 is 7. Value 1 is 42, so V1 is 42. And let's think of this as a TV. It's heavy, but it's valuable, right? And then let's find another thing, and this other thing is going to have a pretty low weight, but a correspondingly low value. So W2 is 3. Value 2 is 12. So this is item 1, item 2. And maybe this is like an Alexa speaker or something like that. So this is a smart speaker. Right? Not as valuable as a TV, but also much smaller. Somewhere in here there's a laptop. Somewhere in between, low weight, high value. W3 is 4. This is not drawn to scale, as you might notice. V3 is 40. There's item 3. And then item 4 is going to be a little bit bigger, worth a little bit less. And we'll think maybe this is some kind of gaming console. So this is the weight is 5, the value is 25. So W4 is 5, and V4 is 25. And this is item 4. So the question is, if my only capacity is 10, what do I bring? Well, the simplest way to do this, and this is not a fast way, but the simplest way to do this is just to perform an exhaustive search. What I'm trying to select is a subset of these items. So let me write down all 16 subsets, figure out what their values are, figure out what their weights are, and then take the one that has the largest value and weight. Okay, so what are our subsets? Subset. Well, we could take nothing, right? That's a feasible solution, right? That fits in our knapsack. We could take just one, and so let me write this in proper subset notation. We could take item 2. We could take item 3 by itself. We could take item 4. And there's our subsets that take only one thing, right? Then we have more subsets. We could take 1 and 2. I'm going to stop writing the braces because it's messy and painful. But we could also take 1 and 3. We could take 1 and 4. We could take 2 and 3, 2 and 4. Or we could take 3 and 4. Or we could take 3 things, right? And so this is 1, 2, 3, 1, 2, 4, 1, 3, 4. We could take 2, 3, 4. Or we could take, and so there's 4 things with 3 items, or we could take everything. 1, 2, 3, 4. And so that's a complete list of all the possible subsets. Now, to understand which ones of these are actually feasible, we have to compute the weights, right? So what are the weights of these subsets? Weight. Well, if we take nothing, the weight is 0. And I'm copying off a list here, but you can double check on the OneNote to see if I'm copying this correctly. If I take just item 1, that's a weight of 7. If I take just item 2, that's a weight of 3. Just item 3 is 4. Just item 4 is 5. And I'm just going to draw some lines so that we keep track of what it is. If I take 1 and 2, that's a weight of 10. If I take 1 and 3, it's a weight of 11. If I take 1 and 4, that's a weight of 12. Okay, so now I've started to write down subsets that aren't actually feasible, right? So these two don't actually fit in the bag, right? The other ones I've written do, but these two do not. So now it's possible that there's a subset that has more things that does fit in the bag. So let me just chase this down and make sure that I write enough that I can, that I have something, have a decent list here. So that's 1 and 4 has a weight of 12. 2 and 3, you know what I can actually do? So I can bring these closer together. There we go. So 2 and 3, if I take 2 and 3, that has a weight of 7. This has a weight of 8. This has a weight of 9. So those two match each other. And then the next ones are 14, 15, 16. 15, 16, 12, and 19. All right. So these are all the weights. You know, some aren't feasible. So not feasible, not feasible, not feasible, not feasible, not feasible, not feasible, and not feasible. So I won't even compute their values, but those are the subsets that I can't take. So that means for any of these subsets that I can, I'll enumerate their values and then take the one with the largest value. All right, so the values are 0, because if I take nothing, I get no value out of it. 42, 12, 40. All right, if I take just item 4, that's a value of 25. If I take 1 and 2, that's 54. If I take 2 and 3, that's the next feasible subset. If I take 2 and 3, that's a value of 52. If I take 2 and 4, that's only 37. And then if I take 3 and 4, that's a value of 65, right? And then nothing else matters because it doesn't fit, right? So these ones are called infeasible. Right. So what's the best value? Well, it's this one. The optimal solution to this particular instance of the knapsack problem is to take items 3 and 4, which in my example is the laptop and the gaming console, and the two together will have a value of 65. And so one of the challenges of this problem is that there are exponentially many subsets. Right? There are 2 to the n possible subsets, and so that means that writing them all down, that doing what I just did here, writing them all down and finding the best would be an exponentially slow algorithm, which means that it would not be something we'd want to do for large values of n. Right? So this raises some problems. And the question going forward will be, how do we deal with those problems kind of in an intelligent, sophisticated way?